Mr. Causey here. Now in this video I give the full solutions to the questions in paper 2 of the SQA's 2024 Higher Maths exam. And I've created question headings for the video. So if you slide along the timeline under the video, you'll be able to find the question that you're interested in. So here's question 1. We're given triangle ABC, we're told it's the coordinates of its vertices, and in part A we're asked to find the equation of the median through B. Now the median goes from B to the midpoint of the opposite side. So these two lines are equal. So the first thing we'll need to do is to find the coordinates of that midpoint. So M, we find the mean of the x coordinates, -3 plus 11 over 2, and the mean of the two y coordinates, 8 plus 0 over 2. And that gives us, there's 8 over 2 is 4, and 8 over 2 is 4. So we've got the midpoint of that line being 4, 4. So next stage is the gradient of that line. So the gradient of the line joining B to M, that'll be, remember it's the y difference, the difference of the y coordinates over the x difference, the difference of the x coordinates. So let's start with the point M. So the y difference, 4 minus -6, and the x difference, 4 minus -1. So 4 take away -6, there's 4 plus 6, that's 10 over 4 plus 1, which is 5. So there's 2. And just check that's reasonable. 1 along, 2 up, 1 along, 2 up. That gradient looks reasonable for that. So we do have enough information now because we know a point on the line. Let's use 4, and we know the gradient of the line, and that's this value 2 that we just worked out. So we'll use our y minus b equals mx minus a formula, where we know that ab in this case is 4, 4, and the gradient m is 2. So the equation of the median is y minus 4, that's y minus b, equals m, that's 2, x minus a, and that's the x coordinate of the point on the line. So let's multiply out the second bracket, that's 2x minus 8, and let's add 4 to both sides. So get y equals 2x, 4 onto the -8 is -4. So there's the equation of that median through B. So let's move on to part B. And this time we're asked to find the equation of this line L, and we're told it's perpendicular to BC and it passes through C. So again, we know a point on the line, its gradient, since it's perpendicular to BC, we should find out the gradient of BC first of all. So again, y difference, 0 minus -6, over the x difference, 11 minus -1. So that'll be plus 6, positive 6, 11 plus 1 is 12. That's 1/2 for the gradient, and it is reasonable. We'll go 2 along, 1 up, 2 along, 1 up. That looks sensible. And therefore the gradient of a line perpendicular to that, remember gradient of a line and times the gradient of a perpendicular to that line would give you -1. So that would give us -2 for the perpendicular gradient. We check 1/2 times -2 does give us -1. And check 1 along 2 down, 1 along 2 down. That's a gradient of -2. Everything seems to be in order there. So what do we know? We know a point on the line. That's 11, 0. And the gradient of the line. I always like to summarise the information that you're using in this formula in case you make mistakes. So the equation of line L is, and again we've got y minus b, that's y minus 0, equals gradient m, that's -2, times x minus a, that's 11, x coordinate of the point on the line. And so let's just multiply the second brackets out. We've got y equals -2x plus 22. So that's the equation of the line L. And finally, let's have a look at the part C in this question. We have to determine the coordinates of the point of intersection of the median through B and the line L. That's this point up here. So let's call that point D. So we have to solve two simultaneous equations. We know the equation of this median line. It was y equals 2x minus 4. We've now found out the equation of this line L, which is y equals -2x plus 22. So to find this point of intersection, we solve these two equations simultaneously. So we solve y equals 2x minus 4 and y equals -2x plus 22. And the easiest way to do that is, since these are both equal to y, we'll set them equal to each other, or if you like, instead of this y, we'll put 2x minus 4 instead of this y. So 2x minus 4 is equal to -2x plus 22. Let's add 2x to both sides, and then add 4 to both sides. So in that case, we've got x being 26 over 4. 2's cancel, that's 13 over 2. And how do we find y? Well, let's use the first equation. So y is twice, we now know x is 13 over 2. Take away 4. And these 2's cancel. And we've got 13 minus 4 for y, which is 9. So the point of intersection that we were required to find is 13 over 2, 9. Now the one last thing we can do is look at this diagram and say, does that really make sense? And there's the point D there. This is 6.5 for x. There's -1. There's 11. So yeah, 6.5 would be reasonable. This point's 4, so it's slightly to the right of 4. I'm just looking at the x coordinates that we know of. So that 6.5 seems to make sense. I'll put 13 over 2 in there. And let's check the heights. This is 9. Well, that's -6. That's 0. The y-axis must be along here. There's a height of 8. So a height of 9 should be just above that height of 8, which it is. So this is looking reasonable. So there's our answer, 13 over 2, 9. So here's question 2. We've got a curve with this as its equation. And we're asked to find the equation of the tangent to this curve at the point where x equals 2. So there's a curve, and we know its equation is y equals 8 over x cubed. And then a tangent is meeting that curve at this particular point. At one point, tangents meet curves at one point, this being called the point of contact. And we know something about this point. Its x-coordinate is 2. So let's try and find the coordinates of that point. In other words, let's find the y-coordinate. So let's set x equals 2 into the formula for that curve, and we get 8 over 8, which is 1. Therefore, the coordinates of that point, 2, 1. So, point of contact of that tangent with this curve is 2, 1. So we've found a point on this line. Next we have to find the gradient of this blue tangent line, and we'll do that by differentiating the formula for the curve. Now, as it is, that formula is not in a state we can differentiate it. We have to get x raised to some power. So laws of indices would tell us if we move this x cubed up to the top of the fraction, it becomes x to the minus 3. That's in a state we can differentiate. So negative 3 times that 8, and take 1 away from that power. That's negative 4. And we'll reverse that procedure and put the x to the negative 4 down to the bottom, become x to the positive 4. So there is an expression for the gradient at any point in this line, on this curve. But it's not any point, it's at the point where x equals 2 that we're interested in. So let's do that. When x equals 2, the gradient dy by dx will be equal to negative 24 over 2 to the power 4. Now 2 to the power 4 is 32, and we can cancel by 8. We get 3 over 4. So the gradient at this point of this curve is negative 3/4, which is exactly the same as the gradient of the tangent line. So find the equation of the tangent. We'll use the usual y minus b equals m x minus a, where the point AB lies on the line and the line has gradient m. So do we know a point on the line? Yes, we do. Point on line is 2, 1. And the gradient of the line, of that tangent line, is negative 3/4. So the equation of the tangent is y minus b, that's the x, the y coordinate of the point on the line, that's y minus 1, equals m gradient, negative 3/4, and in brackets x minus a, that's the x coordinate of the point on the line. Multiplying both sides by 4, we'll get a negative 3 outside this bracket, negative 3 times x, and then negative 3 times the negative 2 is positive 6. I suppose we could add 3x to both sides and add 4 to both sides. So we get 4y plus 3x equals 10. That being the equation of this line. Well, if you have a graphing calculator, you could of course check your answers at this stage by graphing the curve and that straight line to see that it is indeed a tangent to the curve and it does have a point of contact of 2, 1. There's the picture up on the screen that you might get. Now here's question 3, and we're given the coordinates of points D, E and F. There they are. And we've asked to, in part A, asked to express ED and EF in component form. Now just a little reminder that if you have 2 points, somewhere there's an origin, and from that origin to the point A is the position vector of A, and from the origin to the point B is the position vector of B. Now the components of this position vector are exactly the same as the coordinates of the point A. That's true of point B. The components, how you move from the origin to B, the components of that position vector are identical to the coordinates of the point B. Now there's the most important result about moving from A to B. If you travel from A to B, then you can travel that position vector B and then travel against the arrow, so that's negative A. See, there's a parallelogram going on. So travelling from A to B, you can do B minus A. And this is a very, very important result in vectors, one that you should remember. Travelling from A to B, in terms of position vector, is B minus A. Notice the order's reversed. A to B, position vector B minus position vector A. So this is a result we're going to use in part A of this question. So ED, in terms of position vectors, will be position vector of D minus position vector of E. Now the components of position vector of D are exactly the same as the coordinates of D. So they're 2, negative 3, 4. 2, negative 3, 4. And the components of the position vector of E will be exactly the same as the coordinates of the point E. So that's 1, 1, negative 2. And then we deal with each of the components separately. X component, 2 minus 1 is 1. Y components, negative 3 minus 1 is negative 4. Z components, 4 minus negative 2 is 4 plus 2, that's 6. So there's the components of ED. And similarly, we'll do EF in terms of position vectors. That would be position vector of F minus position vector of E. Position vector of F has components 3, 2, 1. And the components of position vector of E, 1, 1, negative 2. So again, we'll tackle each one. The X components, 3 minus 1 is 2. Y components, 2 minus 1 is 1. Z component, 1 minus negative 2, that's 1 plus 2, that's 3. So there's answer to part A. Now let's move on and see what part B asks us to do. Well, part B, part 1, asks us to work out the dot product of ED and EF. Now we've worked out their components. So there's 1, negative 4, 6. Dot 2, 1, 3. And the calculation that's required here is to multiply the X components together, multiply the Y components together, and multiply the Z components together and add the results. So we've got 2 plus negative 4 plus 18, and that comes to 16. Next part of the question, hence or otherwise calculate the size of angle DEF. So let's draw that angle DEF. There's ED and there's EF. I could call this theta, call this vector V, call this vector W. Now, the result we're going to use here is the fact that the dot product has an alternative definition from the one that we were, if you know the components, multiplying the components, corresponding components, and adding like we did there. There's an alternative definition which says you can work out the dot product by finding the length of V, multiplying it by the length of W, and then multiplying that result by the cosine of the angle between the two vectors. So to get the cosine of the angle between these two vectors, we just need to divide both sides by the length of V times the length of W, the magnitude of V times magnitude of W. So that would be V dot W divided by the product of their magnitudes. So that's the result we're going to use, that the cosine of DEF would be the dot product of ED and EF. Well, that's something that we've found already. And divide it by the length of ED times the length of EF, the magnitude of that. Now we have the dot product, we just need to work out the length of ED, the magnitude of ED, and since we have the components of ED, that's 1, -4, 6, we use the formula square root of each of these components squared and added together. So it's 1 squared plus -4 squared plus 6 squared. So the magnitude of this, if you know the components of a vector, square them each and add. So this would be the square root of 1 squared, which is 1, -4 squared 16, 6 squared is 36. So that would be 53 under the square root sign. So it's the square root of 53. Similar calculation we'll do for EF. We know the components of EF are 2, 1, 3. So we square each of these components and add them. 2 squared plus 1 squared plus 3 squared. And that's 4 plus 1 plus 9. And that's 14 under the square root sign, square root of 14. So back up to this formula that we got from over here. The cosine of angle DEF will be the dot product, which we know is 16, divided by the product of these magnitudes. So that's root 53 times root 14. So to do that, we have to find the angle whose cosine is, so the angle DEF is the angle whose cosine is 16 over root 53 times root 14. That's how we read the cos to the -1, the angle whose cosine is this value. So we need the calculator to do this, and here it is. Now, whether you want to work in degrees or radians is up to you. I'm going to work in degrees, so I'm making the mode of this calculator degrees, so it's thinking in terms of degrees. And I want the angle whose cosine is, so that's cos to the -1. I would use the shift button. You might have second function button. You'll know your calculator. And in the brackets here I need 16 and I'm dividing by, now this is a source of error. We're dividing by the whole of root 53 times root 14. We must put that in brackets. So it's root 53, and then we're multiplying that by root 14. And then I complete these brackets. So that's 16 divided by the whole of root 53 times root 14. And then close my brackets for the cost minus 1. And there we go. Let's find out what that gives us. There it is. So the angle required is 54.02 and so on. And that's measured in degrees. So that's approximately, we'll do it to 1 decimal place, 54.0 to 1 decimal place. So here we have question 4. We're shown this graph of a quartic function. That means its formulas involves x to the power 4 and lower powers of x. And the maximum turning point in the graph is -1, 3. We're also shown it passes through the origin there, and it seems to have a point of inflection, horizontal point of inflection, at x equals 2. Now we're asked to determine the coordinates of the maximum turning point on this graph. It's that graph, but instead of x, we've replaced it by x minus 4, and we've added 2 at the end. Now let's have a look at an animation showing the effect of subtracting numbers from x and adding numbers on at the end. What effect do these alterations have on this graph? Now here's the graph from the question, and it's showing the graph of x minus a plus b. I can subtract values from x. Let's subtract 1 from x, and you can see the graph has moved 1 unit to the right. If I continue and I subtract 2 from x, it's moved 2 to the right, 3 to the right, and so on. So subtracting numbers from x moves the graph to the right. On the other hand, if I added numbers to x, take away negative numbers, it moves the graph to the left. But what you want to remember is subtracting positive numbers from x moves the graph to the right. So let's now look at adding numbers to the graph. We're adding 1 to the graph moves up 1 unit. Adding 2 to the graph, it's moved up 2 units, and so on. And similarly, if we subtract numbers at the end, the graph moves down the corresponding number of units. So that's an indication of what happens when we subtract from x and when we add numbers at the end. Now, in the question, we subtract 4 from x, and add 2 at the end. So the graph has moved 4 units to the right, 2 units up. We're asked to find the maximum turning point on that shifted graph. So let's now go back to the question and see if we can work that out. So here we have part A, and we're moving the graph 4 units to the right and up 2. So the point -1, 3 will move to -1, 4, 3 plus 2. X units will move to the right before, and Y up to. So that gives us 3, 5. So to determine the coordinates, the maximum turning on that graph, maximum turning point equals 3, 5. So we'll now move on to part B of the question. And let's have a look at that. We're told that on the diagram in your answer booklet we have to sketch the graph of y equals f dashed of x. That's the derived graph, the gradient graph, if you like, the one that shows you what the gradients are on this graph. So let's now look at an animated version of this graph. So in this demonstration we've got the curve from the question. It has a maximum stationary point at -1, 3. Now for the purposes of the demonstration I've squashed the y-axis a bit, so 1 unit along the x-axis, you can see here 1 unit up the y-axis is about half that distance. So I've squashed the y-axis a bit. But there's the maximum, -1, 3, passes through the origin, and here's a horizontal point of inflection when x equals 2. And I have a point on the curve, and we can see the tangent to that point on the curve. Now the gradient of that tangent measures the gradient of the curve at that point. And in this case it goes 1 unit along, 1, 2, 3, 4, 5, 6, 7 units up. So the gradient of the red curve at this point is 7. And let's move that point to the right. And let's stop about there. And you'll notice that now the curve has a gradient of 1 along, 1, 2, 3, 4, 5 up. And here we've got a point on a new graph. This is the derived graph. This is the graph that shows us the gradient of the corresponding point on the red graph. And if you read that point's y-coordinate, out pops 5. So this point is telling you the gradient of the red graph for this value of x. So let's move that along. You can see the gradients are getting less steep. And at this point we're reading off a gradient of 1. Let's check that corresponding point on the red graph. If we go 1 unit along, we've gone 1 unit up, 1 along, 1 up. So the gradient of the tangent at this point on the red graph is indeed 1. So the derived graph, the graph y equals f dashed of x, the height on this graph is telling us the gradient 1 at the corresponding point on the red graph. Well, let's proceed to this maximum point. And there we go. We've now reached this maximum point, and you know the gradient on that red graph is 0. Let's read off the height of the corresponding point on the derived graph. Well, that's just 0. So you'll notice that the derived graph, the graph y equals f dashed of x, crosses the x-axis at the point where we've got a stationary point. The gradient is 0. Well, let's proceed. We can see that the gradients get negative now. There's a gradient of about -2. And as we approach the origin, you'll notice that that's the steepest that the red graph gets at this point. We've got a gradient of less than -4. And we look at this 1 along, just over 4 units down. And let's proceed past that point. The gradients now start increasing. They get less steep. And you can see that the heights of the points on the derived graph, they're coming back up. So let's approach this point of inflection, horizontal point of inflection. And the gradients are approaching 0. And at the point x equals 2, you can see at this point of inflection, horizontal point of inflection, the tangent has a gradient of 0. Corresponding point on the derived graph, the graph y equals f dashed of x, if you read the height of this point, it's 0. Again, when the derived graph touches the x-axis, we're sure we've got a stationary point or a point of inflection. The gradient is 0 on the red graph. And let's continue. The gradient on the red graph is negative and getting steeper and steeper. So there are a couple of points we can make. Where the derived graph lies above the x-axis, the corresponding points on the red graph show a positive gradient. Where the blue graph, the derived graph, the graph y equals f dashed of x, touches the x-axis, on the corresponding points on the red graph we have a stationary point. The gradient is 0, or a point of inflection. Gradient is 0. These 2 points show that. And where the blue graph, the derived graph, is below the x-axis, the corresponding points on the red graph show the graph has a negative gradient. So above, positive gradients. On the x-axis, stationary points or points of inflection. Below the x-axis, negative gradients. And also another point, we're told that this graph in the question is a quartic graph. That means it has an x to the power 4 in its formula. And when we differentiate to get y equals f dashed of x, we get a cubic. Remember, the power goes down 1. X to the power 4, when you differentiate it, goes down to x to the power 3. So we've got a typical cubic shaped graph here. So let's go back to the question. So here's the diagram from the answer booklet, and on this we have to sketch that y equals f dashed of x graph. Now, stationary points, or points of inflection, the gradient 0 when x is negative 1, and the gradient is 0 when x equals 2. And remember, at x equals 0, this is the steepest downhill gradient that the graph has at this point. So it's quite a large negative gradient, and it turns at that point. And on either side of this point of inflection, the gradients are negative. So it approaches that point, similar to that. And remember, we have to get a cubic, because we know when the quartic, when you differentiate, it gives you a cubic. So let's try and sketch that graph in. So there's the typical cubic shaped graph, and that's our sketch of y equals f dashed of x. So here's question 5. We're asked to evaluate this integral. It goes from 0 to pi upon 7, and it's sine 5x that we're integrating. Now, we know formula sheet contains this table of integrals, and the one we're looking at is sine 5x. In this case, it's a is 5, and we're told it's the negative of cos 5x, but we have to divide by 5. It's 1/5 of that. So we know the answer to integrating, it's negative cos 5x, but there's this factor of divide by 5. And we don't need a plus c because we're evaluating this. We have a lower limit and an upper limit. And what these limits mean is we have to plug in pi upon 7 into this and then subtract what we get when we plug 0 into this. So this pi upon 7 goes in, so it's cosine of 5 times pi upon 7, that's 5 pi upon 7, divided by 5, minus negative cosine of 5 times 0 over 5. Now, this first expression, we certainly need a calculator to calculate that. And remember, if there's no degree signs, we're talking about radians here. So we'll leave that for a minute. Minus negative is positive. Cosine of 0, well, remember the cosine graph starts off at 1. Cosine of 0 is 1, so that'll be 1 over 5. So we're adding 1/5 to this value, whatever it is. So let's bring on the calculator to do this. So here it is. Now, before we proceed, the mode in this calculator is in degrees. We need to change that to rads, radians. So make sure your calculator is working in terms of radians, not in terms of degrees. So let's have a look at the cosine of 5 pi upon 7 of 5 pi divided by 7. Now my pi button is down here. I need to use shift to get hold of it. 5 pi divided by 7. And I'll close my brackets. So there's the cosine of 5 pi upon 7, and that needs divided by 5. Now the whole thing's negative. At the front of this I should have put a negative sign. That's the negative key, not the minus key. Negative goes at front there. So this is evaluated as that. And I now want that answer. And I want to add 1/5. 1 divided by 5. And see what that comes to. There it is. So we've got 0.324 and so on. And that's in radians. So that's approximately, let's just take it to 2 decimal places. Well, here's question 6, and we're showing a graph. Now you'll notice the x-axis is not the x-axis, it's the log 5 x-axis, and the y-axis is not the y-axis, it's the log 5y axis. So we've changed the x and y-axis, but we've got a straight line. We know normally the y-axis intercept, and we can work out the gradient of this line. Now we're told that the variables x and y are connected by this type of equation, y equals a x to the power b. We were asked to find a and b. So there's several methods of doing this. What I'm going to do is pretend, until I don't have to, that we've just got normal x and y axes, and that this line I can now find the equation of it using y equals mx plus c. Remember, that's the gradient of the line, and this is where it crosses the y-axis. So we'll just pretend things are as normal, and then we'll have to deal with these logs in a wee minute. So let's work out the gradient, and we know 2 points on the line. So the gradient m will be the y difference, that's 10 minus negative 2, over the x difference, 4 minus 0. So that's 12 over 4. and that's a gradient of 3. And the y-intercept c equals -2. So we have the equation, well, in terms of x and y, we have the equation being y equals 3x minus 2. So let's now deal with these log to the base 5x and log to the base 5y. So we would have to replace x by log to the base 5x and y by log to the base 5 of y. So what do we get? We get log to the base 5 of y is equal to 3 times log to the base 5 of x, that minus 2. So let's follow the laws of logs here. I suppose leaving a -2 is a bit awkward. Let's add 2 to both sides, and then we'll take away log to the base 5 of y from both sides. Now, subtracting 2 logs, that's fine. We would divide the numbers. However, this 3 gets in the way, but there is a law that says we can move this 3 at the front up and it becomes x to the power 3. So that would imply that 2 is the same as log to the base 5. Now, dividing numbers when we subtract logs, so it's x cubed divided by y. Now, this is a log statement. And every log statement you make, it's like this, number equals log to a given base of another number, can be replaced by a power statement. For instance, there's a power statement, 5 squared is 25. And rewriting that in terms of logs, that's the base, that's the log is 2, and that's the number. So the log to the base 5 of 25 is equal to 2. I sometimes read this as what power do you raise 5 to get 25? And the answer's 2. What power do you raise 5 to get this 25? Your answer's 2. So if we compare this log statement here with this power statement, what power do we raise 5 to get this? The answer is 2. So 5 raised to the power 2 will give you this number, x cubed over y. So let's multiply both sides by y. Of course, 5 squared is 25. So on the left we've got 25y equals x cubed. And divide both sides by 25, we'll get y equals, and I'm going to write it as 1/25 of x cubed. If I divide by 25, I'm finding a 25th of it. And the reason I'm doing that is because we're asked to find a and b when the equation is written in this form, ax to the power b. And you can see therefore that a is 1/25 and b is equal to 3. So that's one way of solving this. There are other ways. Well, here's question 7, and we're given this fairly complicated looking diagram, but certainly 2 curves. There's a upside down quadratic curve and then there's a cubic curve, and we're shown a shaded area there. We're asked to calculate the area of that shaded area. Now the result we use would be from the left hand side of this area when x equals 0 and move along to the right hand edge of the area, that's x equals 2, would integrate with the limits 0 to 2, top curve minus bottom curve. So let's write that down. The area will be given by the integral from 0 to 2, the top curve. Now the top curve is the quadratic one, that's 6 plus 4x minus 2x squared. Subtract the bottom curve. Now that's the whole of this expression. So it'll be minus x cubed, subtracting negative 6x squared, that's like adding 6x squared, and subtracting 11x. So the whole of the bottom curve's equation gets subtracted. So let's simplify before we do any integration. So it's from 0 to 2. Let's look at the x cubed terms. There's only one of them. There's a negative x cubed. X squared terms, minus 2 plus 6 is 4. X terms, 4 of them, minus 11 of them. That's minus 7x. Constants, there's a 6. So that's what we integrate. So let's do that integration now. So we've got negative x cubed, that'll become negative x to the 4. For integrating, we increase the power and divide by the new power. So 4x squared becomes x cubed, and we divide by the new power. X to the 1 becomes x squared divided by the new power. 6 becomes 6x. And because we're evaluating this, we put square brackets, and the evaluation takes place between 0 and 2. And what that means is we plug in 2 into this expression, and then subtract what we get when we plug 0 into this expression. Well, when we plug 0 into all of this, it becomes 0. So in essence, we can ignore that 0, and we just plug in 2. So we get minus 2 to the 4 over 4 plus 4 times 2 cubed over 3 minus 7 times 2 squared over 2 plus 6 times 2. And there's a minus 0. Maybe we should just put in the 0 at the end just to show that we know what we're doing. Now, we can simplify this. On the top of this fraction, we've got 4 2's multiplied together. And the bottom, we've got a 2 times 2. So a couple of these cancel out, and we're left with 2 times 2 on the top, which is 4. So we've got minus 4 for the first term. 2 cubed 8, 4 eighths are 32. So we've got 32 over 3 for that term. One of these 2's cancels with this 2, and we're left with 7 times 2 is 14. That's minus 14 plus 12. Now let's gather the whole numbers together. We've got a minus 18 plus 12. That's a minus 6. And of course 3 into 32 goes 10 times with a remainder of 2. So there's 10 plus 2 thirds. That's 30 thirds plus 2 thirds, 32 thirds, minus 6. I'm going to take the 6 away from the 10 to get 4 and 2 thirds. Or another way of writing that would be 14 thirds. Either way is acceptable. But this is an area we've found the units are, wherever they are, squared, because it's an area. So 14 over 3 units squared for that area. So here's question 8, and we're given a couple of functions in our formula, and we're asked to find an expression for f of g of x. So into the function f, we're going to put wherever g of x is. Now we're told that g of x is x plus 1. So into the function f, we're putting x plus 1. Now, what the function f does to a number x is it squares it, multiplies by 2 and subtracts 18. So that's what's going on to x plus 1 instead of x. We're squaring x plus 1, doubling it, and taking away 18. So we're replacing x in this formula by x plus 1. So that's an expression for f of g of x. Now in part B of question, we're asked to find the values of x for which 1 over f of g of x is undefined. Now, undefined means that we're not able to do this calculation, 1 divided by something. And it means we have to find out when 2 lots of x plus 1 all squared minus 18 takes a value that we're not able to calculate 1 divided by that. Now, the only values that happens for is when we're attempting to divide by 0. Thou shalt not divide by 0, the first commandment of mathematics. It's just a no-no. So this is undefined. For the denominator being 0. So let's try and solve this. If we divide both sides by 2, each term on the left gets divided by 2. Add 9 to both sides. Take the square root of both sides. Now we'll need to watch this, because when you take square roots like this, you could have a negative value. So we'll have positive 3 as a possibility, or negative 3 as another possibility. So we've got to watch out that we take this second possibility into account. So in the first case, if x plus 1 was 3x would be 2, and in the case of x plus 1 being negative 3x would be negative 4. So these are the two values of x where this calculation cannot take place. Now we can check that these are correct. If we put 2 in place of x, 2 plus 1 is 3, 3 squared is 9, 2 9s are 18, we get 18 minus 18, and this would become 1 divided by 0, and that's not defined. Also, if x was negative 4, negative 4 plus 1 is negative 3, negative 3 squared is 9, 2 9s are 18, and this becomes 1 over 18 minus 18, 1 over 0, which is not allowed. So we've found two values for x where this calculation is undefined. Well, here's question 9. Part A, we're asked to determine the coordinates of the stationary points on the curve with this equation. So let's do that. We know that to find stationary points, we have to set the gradient of the curve equal to 0. So for stationary points, we set dy by dx equal to 0. Now, in this case, if we differentiate, 3 lots of a third is 1x squared, minus 2x for the x squared term, and minus 3 for the 3x term, and the constant just becomes 0. So there's our gradient. So for the stationary points, we set it equal to 0. And let's factorise that. Fairly straightforward. X, 3, 1. It'll be minus the 3x plus the 1x. So that's it factorised. First factor being 0, x would be 3. Second factor 0, x would be negative 1. So let's tackle these in turn. When x equals negative 1, I'm now trying to find the y value, and I'm putting x being negative 1 into the y formula up there. So just substituting negative 1 for x and do that calculation. So negative 1 cubed is negative 1, so that's negative 1/3. Negative 1 squared is positive 1, take away that. Negative 3 lots of negative 1 is plus 3 plus 1. So these cancel. We've got 3, that's 9/3 minus 1/3, that's 8/3. So we're asked for the coordinates of the stationary points, so negative 1 8/3 is a stationary point. Now there will be another stationary point, and we'll find that by plugging 3 into this formula. So we get 1/3 of 3 cubed minus 3 squared minus 3 times 3 plus 1. Now, one of these 3's cancel, get 3 squared is 9. 3 squared is 9. 3 times 3 is 9. Lots of 9's around. And 9 minus 9 is 0. Minus 9 plus 1 is negative 8. So 3 negative 8 is also a stationary point. So let's have a look at part B of the question. Hence, use this information to determine the greatest and least values of y in that interval. Now, this is a cubic curve, and large x negative values would be a negative value for y. So we'll probably have a curve, typical cubic curve, that looks like that. And presumably we've found this to be one of the stationary points, and this other one this is a possible setup. Now, if we're asked to find the greatest and least values on an interval like this, well, you notice that negative 1 is the x-coordinate of the stationary point we've got. However, this other one is to the right of 3. Now, you usually find maximums and minimums either at the stationary point or at the end points of the interval. Now, in this case, when x equals 6, we'll have to check if this value up here is greater than the 8/3 that we've got for maximum value there. So let's check that out. When x equals 6, let's find the y value. It's 1/3 of 6 cubed. 1/3 of 6 cubed minus 6 squared minus 3 times 6 plus 1. And 6 times 6 is 36. 3 into the remaining 6 goes 2. Twice 36 is 72. Minus 36 minus 18 plus 1. And when all that is calculated, we end up getting 19. You can check that on your calculator. So we have a value of 19 as the end point when x is 6. So we do have a maximum that's greater than the 8/3, but the minimum value would be negative 8. It's appearing at this minimum stationary point. So we'll state this, that the minimum on the interval, negative 1 less than or equal to x less than or equal to 6. The equals are important because we're allowed to say that it's actually equal to 8/3, and the maximum 19, it's actually equal to that when you put x equals 6 in. So on the interval negative 1 less than or equal to x less than or equal to 6, maximum value is 19. The minimum value is negative 8. So here we have question 10, and we're told that a circle C1 has this equation, and we have to find the centre and the radius of C1. So the method we use, provided we've got the equation in the form of 1x squared plus 1y squared, then we look at the coefficients of the x term and the coefficients of the y term, and these are what's going to be used to find the centre coordinates. So we take the coefficient of x term, half it, and change the sign. That gives us the x coordinate of the centre. We look at the y term coefficient, -2, half it, and change the sign. And that gives us the y coordinate of the centre. And once we've got these coordinates, the radius is then easily obtained by squaring the x coordinate, squaring the y coordinate, and taking away the constant at the end. So that's 81 plus 1 plus 8 under the square root sign. That's the square root of 90. Now that can be written as 9 times 10. Square root of 9 is 3, so that's 3 root 10. So that's part A. Let's now have a look at part B. And there's a picture of C1, so we can add that information that we've got, which is that the centre -9, 1. And also the fact that the radius is 3 root 10. Now, we're sharing this picture of circle C1 with a picture of another circle, and it touches the circle C1 internally at that point. Now, the centres and the point of contact there, by symmetry, would be in a straight line. And what we've discovered in this part of the question is that the radius from this centre negative, let's call it A, centre A, and we'll call B the centre of C2. So what we've discovered is that this whole line, length from A to, we'll call that point of contact C. So it touches internally at C. So this whole line, the radius of circle C1, is 3 root 10. Now, to find the radius of the second circle, which is centre B, we would work out the distance from B to C. And to do that, if we found the distance from A to B and subtracted that from the whole line AC, we would get the radius of circle C2. So let's do that calculation. AB, we'll use the distance formula. That's the square root of the x-coordinate difference squared. That's -9 minus -6 squared. That's the x difference squared. Plus the y-coordinate difference squared. That's 1 minus 0. So what have we got? We've got -9 plus 6. That's -3. When we square that, we get 9. And 1 minus 0 is 1. 1 squared is 1. So we get root 10 for this distance here. Let's put that on. In there, from A to B, we've got root 10. Now, we're trying to find the distance from B to C, and you can see that we'd have to take root 10, 1 root 10, away from 3 root 10, and the remaining distance, that's the radius, is 2 root 10. So the radius of C2 equals BC, which is the full length AC minus what we've just discovered, AB. Now the full length AC from part 1 we got was root 3 root 10. We've just calculated the length of AB to be root 10. So 3 lots of root 10 minus 1 lot of root 10 is 2 lots of root 10. And we're asked to find the equation of C2. So we'll now use x minus a all squared plus y minus b all squared equals r squared, where AB we know is the centre and r is the radius. So we've discovered these values. So the equation of C2 is x minus, now the x coordinate of the centre of C2 is -6 plus y minus b, the y coordinate of the centre is 0, and the radius, well, we discovered that to be 2 root 10. So that's 2 root 10, and we square it. So let's sort this out. That'll be x plus 6 all squared plus y squared equals, now 2 squared is 4, root 10 squared is 10, 4 times 10 is 40. So there is equation of the circle C2 as requested. Well, here's question 11, and we're told the number of electric vehicles worldwide can be modelled by this formula. N is the number of vehicles in millions, equals 6.8 times E raised to the power K times T, and T, we're told, is the number of years since the end of 2020. First off, we have to use this model to estimate the number of electric vehicles worldwide at the end of 2020. Now, at the end of 2020, that's exactly when T is equal to 0. That's when the whole thing starts. So let's calculate that. Number of vehicles worldwide in millions will be 6.8 times E raised to the power K times 0. Now that's 6.8 times e to the power 0. And e to the power 0, any number to the power 0 will be 1. So that's 6.8 times 1, which is just 6.8. So the number of vehicles will be 6.8 million vehicles. So that's part A. Let's move on to part B. And in this case, we're asked to determine the value of K if we know that by 2030, they're estimating there'll be 125 million electric vehicles worldwide. So we know various things. T in this case, we're told, would be 10. That's 10 years elapsed from the end of 2020 to the end of 2030. So T equals 10. We're also told the estimate for the number of vehicles worldwide is 125 million. Now our task is now to determine the value of K in this formula. So let's substitute. 125, that's N, will equal 6.8 times E to the power K, which we're trying to find, times 10. Let's divide both sides by 6.8. So 125 divided by 6.8 will be e to the power 10k. Now that is a power statement, and all power statements can be written as log statements. So this tells us what power do we raise e to. to get this number 125 over 6.8, and the answer is 10k. So our log statement would be to say what power do we raise e to get this number 125 over 6.8, and the answer is 10k. Now that's a direct translation from a power statement to a log statement. If you forget how to do these, try a simple example, for instance, like 3 squared equals 9. Log to the base 3 of 9 would be 2. These two are equivalent. What power do we raise 3 to get 9? The answer's 2. What power do we raise 3 to get this 9? Answer's 2. So these are equivalent statements, a power statement, a log statement. This here is a power statement, this here is a log statement. So therefore, to get k on its own, we'll divide both sides by 10. So we've got whatever the value is of log to the base e of 125 over 6.8 divided by 10. Now, log to the base e is called the natural log, and there's a button on your calculator that you can use to find that. So let's bring on the calculator. So here it is, and here is my natural log button, log to the base e. This button here is log to the base 10. This is log to the base e. So that's the button I'm going to use. And we've defined log to the base e of 125 divided by 6.8. So that's what I've got, and up here, and I have to divide it by 10. So let's work out that, and there it is. So k is equal to 0.2911 and so on. Now let's have a look to see if they want a certain accuracy. No, they don't. So let's just approximate that to 2 decimal places. So 0.29. That's to 2 decimal places. So here we have question 12. We're asked to solve this trig equation and find solutions between 0 and 360, including 0, not including 360. Now, first thing to notice is that in there we have a sine 2x term, and that can be replaced by 2 sine x cos x. That's the double angle formula. So let's do that. Got 2 times twice sine x cos x minus sine squared x. Now, looking at the left-hand side, we can factorise that. There is a factor in common. For instance, if you had 4ab minus a squared, you would take out a common factor of a, leaving you 4b minus a. So that's what's going on here, where instead of a, we're using sine x, and it leaves us with 4 cos x. And then taking sine x from that term would leave us sine x. You can multiply out and check that that factorisation is correct. Sine x times 4 cos x is 4 sine x cos x, minus sine x times sine x does give us sine squared x. Now, a couple of factors multiply give you 0, so that would imply that either sine x equals 0, that's one possibility, or this term, 4 cos x minus sine x, is equal to 0. Now, from the case of sine x equals 0, remember the sine graph starts off at 0 up to 1, back down to 0 to negative 1, back up to 0. So when is sine x equal to 0? Well, it's equal to 0 when the angle's 0, 180, or 360. Now remember, at the beginning when we were reading the question, we said 360 is not allowed. There is no equal sign there. So the only two valid solutions for sin x being 0 in this range are 0 and 180. So that means x equals 0 or 180. So there's two possibilities that we've got from that equation. Now let's have a look at this one. If we add sin x to both sides, maybe write it the other way around, sin x equals 4 cos x. Now at this stage, I'm thinking of the formula sin x divided by cos x equals tan x. But there is a problem. If I divide both sides by cos x, then that could be a dangerous move, especially if cos x is equal to 0. So we'd have to declare that cos x does not equal 0. Now, the possibilities of cos x being 0, let's remember the cosine graph being 0 happens at 90 and 270. Now, you can use your calculator to check whether 90 degrees in there is a solution and whether x equals 270 put in there is a solution. You'll find in both cases that they're not solutions. So we definitely know that cos x is not equal to 0 and that we're not missing out solutions in that case. So at this stage we can say that tan x is equal to 4, a positive value. And if you remember your quadrant diagram, CAST, where is x, which quadrant is x in for the tangent to be positive? Well, that's the first quadrant and the third quadrant. So first and third quadrants. So what is the angle whose tan is 4? That's how I read tan to the minus 1. It's the angle whose tangent is 4. And we'll need to bring on the calculator for this one. And here it is. So we must make sure that your calculator is reading degrees, which it is in this case. Tan to the minus 1 button on my calculator is up here. I'd use the shift key. You might have a second function key. You'll know your calculator. So there's tan to the minus 1. And we put in the value 4. That gives us this angle. So x equals 75.96 and so on. That's the first quadrant angle. Or, now to get into the third quadrant, we'd need to take 180 plus the first quadrant angle. So let's take 180 plus that answer, and that gives us 255.96 and so on, or 255.96 and so on. Now, we're not told what accuracy to give, so let's just do it to 1 decimal place. And let's put them in order. Solutions are x equals 0, 75.9, if we take that to 1 decimal place, be 76.0. Next up's 180. And finally 255.9, that would go up to 256.0 to 1 decimal place. So that's to 1 decimal place where necessary. Some of them are exact, 0 and 180. So that's it. These are the 4 solutions in this range of values for x that satisfy this trig equation. So here's question 13. We're given a graph, it's a quartic graph, various bits of information about that graph given, and we asked to find the formula for that graph in this form. So let's write this down. F of x equals some number k times x plus a all squared times x plus b times x plus c. So we've got a whole bunch of factors multiplied together. Now what we should look at is, when is the value of f of x, this expression, when does it equal 0? And we'll find that on the graph by the points that touch the x-axis. This point's interesting when x is 3 because it's tangential to the x-axis. It comes up and touches, then goes back down. That would imply what we call a repeated root, and the root 3 would therefore be associated with this factor that's squared. The root -1 will associate with this factor, and the root 5 will associate with this factor. Now, how does that work? Well, we certainly don't know k yet, but when we set this equal to 0, we're supposed to get a 3 from this expression. That would mean we have an x minus 3 all squared, because when we set x minus 3 equal to 0, we'll get out a root of 3, a value of x that's 3. Similarly, for a root being -1, we would have x plus 1 in there. When we set x plus 1 equal to 0, out pops -1. And finally, for a 5 for a root, we would have a factor of x minus 5. When we set x minus 5 equal to 0, out pops +5 as the root. So far so good. The one thing we don't know is this factor k at the beginning. Now, we've used the information of these 3 roots. The other piece of information we're given is that when x is 0, the value of this function is -9. So we can say when we put 0 into f of x, out pops -9. So what does that mean? Well, let's plug 0 into this formula. We've got k times 0 minus 3 all squared times 0 plus 1 times 0 minus 5. And we know from the graph that -9 is the value. So let's simplify this. K times -3 all squared is 9. That factor's just 1. This factor is -5. And that all comes to -9. So we've got k times 9 times 1 times -5 is -45. And let's divide both sides now by -45. So that will be positive, and there's a factor of 9 in 45. We cancel factor of 9, we get +1/5 for the value of k. Now we're asked to express that in this form, so we must do that. We haven't quite expressed it as such, because now that we know k is 1/5, we'll put that in there. So we get f of x finally being 1/5 of x minus 3 all squared times x plus 1 times x minus 5. So that's your final answer. So that's Mr. Corsi signing out, and I hope you enjoyed the video.